So I'm going to talk about the RocketScience application. It's in Games Directory, RocketScience. So somebody thinks I'm in the IRA and I'm in some kind of prison with no email or some shit, I don't know. Anyway, lovely. So you control the feedback on a rocket, and if you do, you can make it high gain or low gain feedback. So where should we start? Settings push, settings pop is for all applications. That basically, as it turns out, when you're at the command line and you include something, it doesn't spawn a new task. It's the same task. And therefore, if you run something at the command line, then it returns you to the so after we run this, we're going to be back at the command line. We're back at the command line. Anyway, it's the same task. It's sitting in memory. So if we say who -r, these are all the symbols from the RocketScience application. This is the same task. Anyway, so somebody wanted me to explain every line. Okay, so we make the background yellow. We get rid of the cursor from the command line. This, as a matter of fact, is solid text. We print spaces or carriage returns in order to make the background. We could use, we don't have to do that, but that's what we do. So this part right here, light cyan, is the background, and then we do a %C repeating a character n times. That's a special %F code. So we do window height -4. So we do carriage return. That's with the cyan background, and the rest of it will be yellow because we set it up here. Menu push, menu pop. When we run this, we have a menu up at the top. Restart. That didn't seem to work. Restart. It's waiting for a key. Okay. Restart. Okay, so we have a menu, abort, exit, abort. Oh, it's waiting for a key. Every time it runs, it waits for a key, and that gobbles the exit key. So these are how my menus work. They have ASCII or scan codes. These are all ASCII. Shift Escape is an ASCII 28. I invented that. Space, carriage return. So we use my differential equation engine that I got from the book Numeric Recipes in C. And if you want, you can study the code. It's in the Atom directory. Math ODE, where is it? So it's built into the window manager, and the window manager runs 30 times a second, and every time it runs the window manager, It also updates the differential equations, and they have a t variable in the control structure for differential equations, and the time is real time, so t passes at real time. That's how it calls it from the window manager. What this is a run cut of 4-5 adaptive step size algorithm. It's pretty much adapted out of numeric recipes in C. So there's a derivative function callback that you're supposed to use. I added some built-in I added masses and springs as so that you don't have to do those by hand. I wrote an application called SimStructure that was really deluxe. Anyway, and it had masses and springs and thrusters and foils and guns, and that was the year 2000. It was pretty impressive at the time, but now you have Grand Theft Auto and all of that. Anyway, the one thing it doesn't have is friction. That's really hard to do. When you supply a derivative, you have to figure out the normal force on the surface and then find friction or something. Anyway, I didn't do that. So masses and springs and thrusters and stuff are pretty easy. Anyway, so this sets up a one of these differential equation control structures. You tell it it has a few more things built into it, like viscosity, drag, whatever you want to call it. When it moves through air, you have friction slowdown. Oh, when I said friction, I was not talking about air resistance. I was talking about against a ground surface. Anyway, so it has masses and springs, and the way this is modeled is you have a rocket with a top and a bottom mass, and the airplane. I don't know why the airplane needs a derivative. It doesn't accelerate, it just flies. But anyway, so the SimStructure application just had circles for masses, but what we do with this is we make a sprite and we put it on top of the mass. So there's actually two masses for the rocket, the top and the bottom. And anyway, so these masses are global variables. In SimStructure and other places, I dynamically allocate masses so that, because you don't know how many masses you're going to have. There's another application called hey, I could make this. Never mind. There's another application called Strut, which uses, it's very, very similar. So you place masses and springs, and this has variable number of masses. In the RocketScience, we had three masses, or two for the rocket and one for the. Okay, I'm going to make a connector that breaks when you press 1. So, okay. Now I'm going to make a connector that breaks when you press 2. Now I'm going to make a thrust. Oh, let's do a few more springs. Now I'm going to make a thruster. So SimStructure was like this, except it was. Anyway, that's too bad. Okay. So we run this, and 3 are those engines. Number 1 will break that, and number 2. Anyway, so anyway, getting back to the rocket science, we have just a fixed number of masses, and we have one spring connecting the top of the rocket and the bottom of the rocket. I can show you in the differential equation code has the it calculates a spring force based on how much different or how much displacement from the equilibrium you set. Anyway, and it inserts there's a Q. You can have multiple of these differential equation control structures. FS is your task register. That's the current task. So once you insert this into the queue, then the window manager will find it and update it real time. It's nice to keep the time passing in the ODE same speed as real time. You can actually set it to go faster or slower, I'm pretty sure. Anyway, so the main thing you have to supply is a derivative callback. So here's the derivative callback. We set the derivative right here. This is where we set the callback. In Holy C, you have to put an address before a function pointer. Anyway, so state num. Okay, well we have 3. Oh, I'm sorry. We have what is that? I think it manages the masses by itself. You don't have to count the number of states. State num 2. Oh, okay. What? The nozzle angle and the nozzle velocity. I think we're integrating. Maybe we're doing a PID controller. There's obviously two. There's obviously X, Y, and Z. Well, there's no Z, but for each mass you have an X and a Y, and you have a derivative of X and a derivative of Y. So we have a lot more states than just 2. There's a state vector, and maybe it might have been foolish to think other people could use this code. A lot of times just writing it from scratch is the wisest thing. But anyway, so basically you have when you make those masses, it allocates states for those, and what are these other states? Nozzle angle. I don't think I did a PID. I did a derivative. Oh well, let's find out. Well, first of all, we have a draw it. This just puts the sprites on top of the masses. Since my masses are global variables, it's really easy to access them from the draw it. The other thing we have to draw is the smoke, and it turns out that I put it onto the persistent layer, which the persistent layer is kind of for kids. One problem, watch this. So I got excited when I realized I could pan the screen, but the smoke doesn't pan. So I was going to go chasing. I was going to make the rocket loop around and chase the plane after it did a loop. You could anyway. If it misses. So the problem is the smoke is on the persistent layer. If we really wanted the smoke, we would have to make an array and store all the XY of the smoke and then move the smoke around. Anyway, that's where it makes the smoke. There's no reason that we have to do this in the draw it. This could be asynchronous. It's accessing the persistent layer. I think we must have made an alias for the device context. Yeah. So DC2 is the persistent layer somewhere down here. That's an alias for the persistent layer. Anyway, so what else we have here? Window max, that maximizes the window. Remember, we start at the command line, and then it maybe you have, anyway, it maximizes the window, gets rid of borders. I think it does, doesn't it? Anyway, task end callback. Okay, so I was conscientious. I don't know why I bothered to do that. I don't know why this is here, to be quite honest. Oh no, we made our own task end callback. Then I thought that was a standard. Sometimes there's a couple standard callbacks you use. Okay, we're erasing the persistent layer and we're turning off sound. If we get a Control-Alt-C that aborts, we want to erase the persistent layer. Oh, we would, if we kill this task, we're actually telling it to erase the persistent layer. This is for if the task gets killed. This is not just a Control-Alt-C. This is a Control-Alt-X, which kills the task. That's task callback. You know, as a matter of fact, I don't even know if I reset the... I don't know if I clear that. I don't think I do. The settings push and pop keeps track of a lot of things. It doesn't mess with that callback. Anyway, so what else we have here? We set the draw. This is for the window manager callback. We looked at the routine up above. So the game loop just gets a character. We don't have to get keys. We're not using the cursor keys. We're just checking for a few that happen to be ASCII. Since the keys we're looking at are ASCII, then we can use get char. Otherwise, we say get key. And we're not doing any mouse or anything like that. So otherwise, we would do get message. So we have to be sure not to get interrupted. And that's why we have this preempt. We're turning off preemption. It gets turned back on because we saved the state in the settings push. And so since we can't get preempted, we don't burn CPU time because we're waiting for characters, and that swaps us out. So it's okay to have preemption off. So in other words, what this turning off preemption does is it says all the code from here down to here does not get interrupted, and the window manager will not get inserted, we will not yield, the window manager task will not run in this part of the code. So we're safe to change queue links. I almost always use doubly linked lists, and when you insert the differential equation engine, the links are in flux. There's two links, so it's not atomic, and that's why we turn off preemption, so that the queue links don't get corrupted. So as a matter of fact, we do not get, it will not preempt us all the way down to this settings pop. So these queue links can be changed, and the window manager will not know the difference, or it will not interrupt. We can delete the ODE at our leisure. Normally I make a cleanup routine. I make an init and a cleanup. Normally I would put the delete into the cleanup. This is a global variable also, isn't it? Anyway, oh well, it doesn't matter. Menu pop, this is the menu. These get pushed and popped. So when we go back, guess what the menu is when you're at the command line? The command line has a menu. So we return to the command line menu. Anyway, so let's look at the rest of this. What else do we have? We initialize, we basically put the rocket at the bottom, and what do? We set the spring length to the distance between the two masses, I hope. Rest length. Okay, we have that hard-coded as, anyway, DVT span. That doesn't sound like a very good label. I don't even know what some of these labels get the name changed by accident. I don't know what I have no idea what DVT is supposed to stand for. Anyway, in my operating system, I changed names. This might have got clobbered accidentally. I don't know. What do you think DVT stands for? Derivative type? I don't know. Oh well. Anyway, that's the height of the rocket, 40 pixels. We went ahead and kept the coordinate system as pixels, I do believe. When you're doing something like this, a lot of times you work with meters instead of pixels. When I did sim structure, I worked with meters, and then I set the scale to convert to pixels. I think this is pixels. Anyway, what's left? So did we talk about? We talked about the draw it. We draw some lines. What are these lines? M1. I don't even know what that is. Yellow and red lines. If it's black, oh, that's the fire. We draw 6 triangles of fire that alternate between yellow and red based on every time the window manager updates, we increment this. And so what's going to happen is on odd and even window updates, we do red or yellow. So let's look at the fire. So we have fire that's red and yellow. That looked like red and yellow. It didn't look like all red and then all yellow. So in order to do a triangle, you work with the nozzle angle. Arg, when you're working with polar coordinates, arg will convert to an angle based on an XY. So the vector difference between the bottom and the top of the rocket, take the arg, which converts to an angle, and so that's our angle theta. And I is we're drawing six triangles that are bigger, biggest. 6, so that makes a solid triangle. I'm surprised I didn't alternate. Oh, I XOR the update. Okay, that's what I knew that. So not only is it's every other update, it changes, and also there's 6 triangles in a row, 2 lines to make the point, and then we make on top, we only do this after it's blasted off. That's a global variable. And then we make the smoke, and if the plane is hit, then we draw sprite number 2. These are the sprites up here. If we do Control T, we'll see we have sprite 1, sprite 2, sprite 3. So sprite number 2 is the explosion, and it keeps moving forward as it should. If we check for a collision between the rockets, so first we draw the plane, and then we do a collision check to see if it has collided by drawing the missile, and this will get pixel overlaps. And we set the plane hit, and we make a noise. Noise spawns a task that makes noise. This is handy. We don't have to. All we have is a frequency on a speaker, and this is handy that we can fire and forget. This makes a task that handles all our troubles. It has a callback if it gets killed. I don't remember if this is a child of our task, so if we die, it dies. I don't remember. I think so. I think if we die, the noise dies. These are the issues that make it difficult. Anyway, so sound, we're setting a, I think this is a 50 hertz. If collision is greater than 100, plane hit. Oh, this is just the rocket engine has a tone when it's flying, and if the plane is not hit, that's kind of weird. If plane is not hit, we turn off sound. If it is blasted off and the plane is not hit, then we play the tone. Otherwise, if the plane is not hit. Okay, so we don't want to turn off. Anyway, simple stuff. So finally, we draw the image itself. We drew it once in order to count collision pixels. That was invisible. And now we draw it again. And we draw some circles. What are these? Oh, this is the target. When I made my missile control system, I calculated how far I had to lead the target. That's the velocity times the distance you are from the target. So we set an X and Y for our target based on how much we're leading. So that's the circle. If you watch when you see the circle, that's what we're aiming for. And once we're in the air, then it locks on. Okay. You can do these a lot of different ways. It's not very accurate. I just did so you would have to calculate the exact time it gets in that spot. I just did a simple distance from the plane divided by the speed of, but the rocket accelerates, doesn't it? So I don't know. I don't even know how I approximated that. Anyway, so now we're getting to the derivative. What are we doing here? Unit vector pointing to the top of the rocket from the bottom. Okay, so we have CD3, which is a class for 3 dimensions. D, I think, is double. I've run into some problems when I changed from standard names. Maybe I don't know what. Why do I call it D3? I guess it's dimension 3. Oh, it's not double, it's integer. These are I-32s. Okay, that's kind of weird. I thought most of the math is float double. Inside the... now I'm confused. I could swear it's all float double. Inside the differential equation. Oh, it is. I jumped to the wrong symbol. Okay, it's float doubles. Okay, so we set a float double. This does some vector math. We subtract 2 vectors. The x is the first variable of the state. We're past. Okay, there's the ODE node has a bunch of individual allocations for all the masses. Actually, they're all linked together. Do you remember? They're global variables. In other programs, they're dynamic. And then what it does is the derivative goes ahead and combines them into a state vector. So we have a state vector and a derivative of state. And those are what you're supposed to use. Now the mass has a pointer back to the state array. Okay, so this points back. No. See, it's constantly copying between the state vector and then all these. It's constantly copying between the state vector and all these nodes, which are just nodes. Anyway, so I don't know what I was thinking. I'm the only one who can understand this. I might have wasted my time. I never use libraries if I can write it from scratch. Anyway, so He copies between the state vector and the nodes, and whatever. Anyway, so I don't even think we use the state vector that's passed to this callback. We just use the global variables that have the updated state. Sometimes you want an initial position for the vectors and then the actual position. Anyway, as a matter of fact, we're using the built-in data type CMass. Here it is. It's got Q links. It's got pointers to state and dstate. And then it has the mass has the mass, and it has, okay, when you save this to disk, you go from start to end. No, that's when it copies to the array, I think. Anyway, so I don't think anybody else understands this, so I wasted my time making it a library. It's hopeless. That's kind of depressing. Anyway, so there's some now what you do is you make your own class and you expand. You make a base class with the built-in mass and spring. I do that in some of my applications, like I add a color for the springs and stuff. So what are we doing? We are, oh, this goes forward order. This goes 1 by 2 and store it in P-body. That's funny. So I use P for my vectors. So it's calculating the it's making a vector that points from the top to the bottom or bottom to top. Then it's converting it to a unit vector. You always have, I don't remember if all of my, this is going in one direction. A lot of my math routines go the other direction and put the destination first. You just have to look it up. So if we look up this routine, vector 1, vector 2, and then the difference. So some of them go one direction. Oh well. I don't have C++, so I can't do operators. So what are we doing? D theta dt. Let's just prevent 2 spin. I think I meant to say too much spin. Okay, yeah. So we have we calculate the derivative of the angle of the rocket, and then what we do in order to keep the rocket flying, this acts kind of like a gyroscope or something. We want to keep it going in one direction, and so when we're setting the thrust vector direction, then we have a term that wants to keep it from changing its angle. It's kind of like a gyroscope. You know how a gyroscope doesn't want to change its angle? The term that we're going to add, d theta dt, desired nozzle angle. So we're doing a weighted, you have these various coefficients that weight what you're doing. So we're kind of partially torn between turning the nozzle to angle at the target, but we don't want to turn too fast. And I imagine that the pixel coordinates of these two are wildly different, and so that's why, even though this is a lower gain than this, the units are radians, derivative of radians. The units here are target angle error. Okay, so we're dealing with the derivative of in radians of theta, and then the target angle error. Okay, well, anyway, so what are we doing here? Now we're copying the P target. Where did we calculate that? Okay, from the top to the target. So we make a vector pointing from the top to the target. We take the distance. Okay, we want this distance for various usages. So we before we normalize, we get the distance. So we do another copy. Then we make it a unit vector. And v, what is v? It's some kind of velocity, isn't it? What are we dealing with here? Acceleration and velocity, or something like that. We don't control the rocket speed. I think we just go full throttle. We just control the angle. You talk about controllers that are single input, single output. When you have a signal for nozzle angle and a signal for thrust, then it's multiple input, multiple output. And sometimes they have to, sometimes they're, what's the word? I'm just reviewing some of my terminology. I studied control systems for 2 years. If they're coupled, then you have to, I didn't solve these with anything I was taught. I just did monkey. I just acted like a monkey and set the feedback gains to make it fly. I played, anyway, let's, collision estimated t. So we take the velocity divided by acceleration. Normally this would be a quadratic, wouldn't it? Discriminant. I actually do. Okay, it's a second order equation with velocity and acceleration, and I'm estimating my time to hitting the target. I didn't think it was that sophisticated. Aim for projected position of plane at time of impact. Okay, so we're leading the target. I think we set that global variable. Isn't there a global variable? My debug. I wonder what that is. Oh, so we can display a value by shoving it into that. Anti-spin coefficient. Why don't we, where's that CX, CY? Oh, that's the center X, center Y. You can make it track the center, that's the center of the, okay. Oh, when we're drawing the sprites, we're doing them relative to the center of the screen. Okay, one time I made it track when it went off the screen. I thought we have to draw that circle. M3. Do you suppose that's the? It's not the plane. The plane is. Maybe I made that M3 into the target position. The aim. I guess you'd call it the aim point or something. I don't know why I don't know if it's the plane, or I don't know why that has a state. I think if it's just a constant velocity, you almost don't need it. Oh well. So we went through all that trouble to calculate the acceleration and velocity. I'm surprised we didn't store that and use it for the circle. Okay, what are we doing? Aim for the projected position. I don't know what we're doing exactly. I think we're setting the nozzle angle to the aim point with the feedback to keep us from spinning too much. So we have a derivative, which is the spin in radians, omega, something like that. Anyway. And so the whole purpose of the derivative is to set the derivative of the state. And that's what we're doing here. We're setting, okay, so we have a nozzle angle, and because everything is second order, you almost always have two states for things. F equals ma is second order, so, and okay. So this only starts happening when we blast off. Okay, here's where we're setting. This is kind of, these pointers point back to the state vector. So we have a state vector which has those masses and angles, and then this member variable points back to the state vector. There's a single array, and what it has is mass 1x, mass 2, mass 1y, derivative mass 1x, derivative mass 1y. It has all those. Anyway, I think we covered everything. I'm just a little bit confused because I could swear that we would not. M3 must be the aim point. I guess we have to. I guess we input the airplane. I think the position of the airplane is handled by the derivative. Let's look for M3, see where it is. Oops. We move the airplane. Okay, so we're drawing the plane at the M3. What about the circle? The circle is the red circle. Target X, target Y. Okay, that's what I was. Now that's what we're talking about. Okay, first of all, where do we subtract? P target is the vector. So we're putting the target. We're making a vector for X and Y. I want to see where we. So we're copying. Okay. Oh, do you know what? It's a constant. dx dt is a constant. There's the velocity. I'm kind of surprised that I guess it doesn't change. So when we make the initial node, we set that as a constant. And target X is a global variable. Target is a CD3, a three-dimensional. Okay, now everything makes sense. So we set target X and target Y. Once we've gone through all that work to calculate the velocity and acceleration quadratic, then somewhere we're going to set target X, target Y. Here's where we're doing it. Let's see. P target. Let's look for, we're going to look for target as a whole label. Target. We draw the target. Okay, so we copy P target into target. I guess I didn't want to. You know, technically, what if it got interrupted and you drew 1x and 1y different? These happen to be, the window manager handles both drawing and the differential equations. The window manager calls the drawback to draw. It also calls the drawback to the differential equation. So as a matter of fact, it doesn't have to be atomic. You might not want it to draw if it set the X and then changed and set the Y. That would be bad. Anyway, as a matter of fact, okay. Anyway, I think we've covered this sufficiently. So how about that?